All right, for the first problem on the worksheet, it says consider the radial field F, which with components just x comma y comma z, and notice that's just the position vector of the point whose coordinates are x, y, z, and we have the sphere S of radius a centered at the origin. Assume that S is oriented so normal vectors point outward. Compute each of the corresponding integrals in the divergence theorem to verify that they are equal. All right, so we'll start with the flux across the boundary. And here, since our vector field F is a radial field and we're integrating over a sphere centered at the origin, I actually want to show you two ways to compute this. The first way is to use the parameterization of the sphere just from the surface integrals worksheet, but as we're going to see, that's a little tedious. So here's the parameterization for the sphere, again, just straight from the worksheet. And so here's our normal vector, right? And so to compute this flux integral, well, I'm going to integrate over this rectangle in the UV plane where u varies from 0 to pi and v varies from 0 to 2 pi. And we're going to integrate this dot product where we have f of r of u v dotted with this normal vector tu cross tv. And for f of r of u v, since f is just r itself, it's just the position vector, this part is simply equal to this position vector you see here from the parameterization, a sine u cos v, a sine u sine v, and a cos u. And then here is our normal vector. And so this is pretty messy right here, but fortunately it does clean up quite a bit. So I have an a squared here and an a from this vector. So I'm going to factor out the a cubed. And then we're going to get this sine u out front. And then in parentheses, we have sine squared u cos squared v plus sine squared u sine squared v plus cos squared u. And see from the Pythagorean identity on these two terms, these sum to just sine squared u. And then we have a sine squared u plus cos squared u. And so that all simplifies to just 1. And so 1 times sine u gives us sine u. Okay, so then computing this integral, which is not hard, is just 4 pi a cubed then for the flux across the boundary. All right, so now as another approach, okay, here we want to note again, since our field is a radial field, and our surface here is just a sphere centered at the origin, the unit normal vector is really just the position vector r divided by its magnitude, right? It's just the unit normal vector in the direction of r. And since we're on a sphere of radius a, this magnitude is just constant a. Okay, so that if I take the dot product of my vector field f with the unit normal n, I'm just taking r dot r divided by a, and r dot r is the magnitude of r squared. And again, since we're on the sphere of radius a, this is just a squared. And then if I divide that by a, it just simply gives me a. Okay, so a constant dot product over the sphere, which is very, very nice. And so computing then the integral of just this constant over the sphere would give us a times the surface area of the sphere. So a times 4 pi a squared is again 4 pi a cubed. Okay, so certainly recommend this method. It's quite a bit simpler. As I noted back in section 15.6 on surface integrals, this is typically the approach often seen in a physics course on, say, electricity and magnetism, because there it so often is the case that this dot product turns out to be a constant, okay, because of things like radial symmetry and that observation really greatly simplifies calculations. Okay, so let's now go ahead and turn to the total flux throughout the solid ball. And for that, well, it's actually a heck of a lot simpler than both of those flux calculations that we just computed over the boundary. So for the flux throughout the solid ball here, we want to compute the triple integral of the divergence of the field over the solid ball. And the divergence here is just constant 3, right? We're taking the x derivative of x, which is 1, and then the y derivative of y, which is also 1, and then the z derivative of z, which is also 1, so that sums to constant 3. So this triple integral then of 3 over the solid ball is just 3 times the volume of the ball, and that then is 3 times 4/3 pi a cubed, right? Because it's just a ball of radius a. And so that again gives us this value of 4 pi a cubed. All right, great. Well, that's going to do it for this question. Thanks so much.